Sklearn inspection partial dependence. Description partial dependence plots PDP help visualize the marginal effect of a feature on the target variable, keeping all other features constant. It provides insights into how a specific feature influences the prediction. Inputs: model a trained machine learning model, e.g., decision tree, random forest, neural network. Feature: the specific feature you want to analyze. Data: the dataset used for training the model or a subset. Outputs: PDP plot a visual representation of the feature's impact on the target variable, typically showing the average predicted value across different feature values. Feature values: the range of values of the selected feature used for plotting the PDP. Steps: feature selection: specify the feature you want to analyze. Grid creation: create a grid of values for the selected feature. Prediction: for each value in the grid. Predict the target variable for each observation in the data, while keeping all other features constant. Average prediction: calculate the average predicted value for each feature value in the grid. Visualization: plot the average predicted values against the corresponding feature values to create the PDP. Metrics: non-PDPs do not directly measure a specific metric, but they visually depict the relationship between a feature and the prediction. Visualization plots: PDP plot: a line plot showing the average predicted value against the corresponding feature values. This plot helps visualize the effect of the feature on the target variable. ICE plots: individual conditional expectation plots show the predicted value for each individual observation as the selected feature changes, providing more granular information than the average PDP. Fine-tune parameters: grid size: the number of values in the grid for the feature. A finer grid can provide more detailed information, but may require more computational time. Feature values: you can specify a custom range of values for the feature instead of using the entire range from the data. Percentiles: specify percentiles to determine the feature value range used for the PDP. Uncertainty methods: non-PDP itself doesn't provide uncertainty estimates directly. However, you can use techniques like bootstrapping or permutation tests to quantify the uncertainty in the PDP estimates. Challenges and fixes. Challenge 1: high-dimensional datasets. In datasets with many features, PDPs can become difficult to interpret, as the marginal effect of one feature might be influenced by interactions with other features. Sample use case: a model predicting house prices with 20 features, where the PDP for number of bedrooms might be confounded by interactions with location or square footage. Fixes: feature selection: prioritize analyzing PDPs for features that are deemed important based on feature importance scores or domain knowledge. Partial dependence: with interactions, use techniques like the individual conditional expectation, ICE plots, or generalized additive models (GAMs) to explore the interactions between features. Challenge 2: nonlinear relationships. PDPs might not accurately represent complex nonlinear relationships between the feature and the target variable. Sample use case: a model predicting customer churn where the relationship between age and churn might have an S-shaped pattern not easily captured by a linear PDP. Fixes: nonlinear models. Consider using models that can capture nonlinear relationships, e.g., decision trees. Support vector machines with nonlinear kernels. Advanced PDP methods explore methods like Friedman's edge statistic for a more nuanced analysis of the interaction between features. Challenge 3: high cardinality categorical features. PDPs can become difficult to interpret for categorical features with a large number of distinct values. Sample use case: a model predicting product sales with a category feature that has hundreds of different product categories. Fixes: feature engineering: consider transforming high cardinality categorical features into lower dimensional representations, e.g., using one-hot encoding, hashing, or embedding techniques. Grouping categories: group similar categories together to reduce the number of distinct values. For easier analysis, partial dependence plots with binned features use methods to analyze PDPs for features that have been binned into categories.